We can now move into the unit which one will come across in most EVs owing to the characteristics of the motor. If you observe the RPMs at which the wheels rotate and the RPMs at which the motor rotates are very different. The wheel RPM is much slower than the motors. We need to introduce a reducing mechanism which can reduce the motor RPM. As the law of conservation of energy remains true, because of the subsequent action, the effect is that the torque at the output of the reduction mechanism is increased proportionally. The operating RPMs for the motor hover from 0 to upwards of 12,000 RPM. The RPMs required at wheels with around 0.7 meter diameter will be 450 RPM for 60 kilometers per hour. The maximum torque required at the wheel varies on multiple factors like the diameter of the wheel, the weight of the vehicle, amongst others. And that ranges from 200 Newton meter to 500 Newton meter for a stock car. There are primarily three types of reduction mechanisms: gearbox, belt pulley and chain drive, of which belt pulley arrangement is not widely adopted for its efficiency and shorter service life. Chain drives have lesser load capabilities compared to the geared counterpart. They are also prone to noise and affect the NVH in a car, which leaves us with a gearbox which is most widely adopted. The required reduction generally hovers around 10:1. Well, how we reach the exact ratio is something we will take up shortly. But this range of 8:1 to 12:1 is manageable with a single or a double stage gearbox, where you have two pairs of reduction which end up multiplying with each other to give us our final drive ratio. The gear used are spur or helical. In cases where hub motors are used, a planetary gear system is also observed. Before we get into a detailed understanding of the drive ratio, let's understand what a differential is. Now this reduced RPM must be supplied to a minimum of two wheels either on the front or the rear. While taking a turn, the inner wheel of the vehicle will rotate lesser as it is tracing a smaller radius circumference, while the outer wheel will spin more because it will be tracing a higher radius circumference. If we try to mount them on a single shaft, then one or the other will slip, thus causing a higher wear and tear of the tires and also lesser control on the dynamics of the vehicle, where this phenomenon will lead to understeer, or what we colloquially call as drifting. Thus a mechanism called as differential is added. The differential allows two wheels to be driven by a single prime mover but still allows them to rotate individually. Thus, where systems which have only one motor for two wheels, or in cases even for four wheels, a differential is adopted. The final drive ratio of the drivetrain is one of the most crucial aspects, especially in a single speed transmission. Fine-tuning of this value to the second decimal is a commonplace. This ratio will determine the trade-off between acceleration and top speed. In general, a lower final drive ratio will lead to less torque at the wheels but a higher top speed. Meanwhile, a higher ratio will result in the opposite, that is more torque at the wheels but lower top speed. Remember that this is done without any change to the power and torque of the prime mover. It will define how efficient your vehicle will be. This can be said to be one of the most sensitive values in all of the vehicle engineering, along with weight, wheelbase, wheel drag coefficient, etc. Well, this ratio is all about optimization and is very case dependent. It all depends on what application it will be used in. The input power is also a great matter of concern. There is no thumb rule of the bigger the better or smaller the better. When there are multiple varying values associated and we need to optimize, we turn to mathematical modeling. Something as primitive as an Excel sheet with basic formulae can be a great tool to start with. There are many complex modeling tools like MATLAB where we can literally build each and every component of a vehicle. For illustration purpose, such depth is not required. We can pick up a simple lap time simulator like Optimum Lap, a software from Optimum G. Here you can create tracks, car models, and simulate them to take a lap around circuits which you have built or have imported. The major objective of this exercise is to do the sensitivity analysis of the FDR on the vehicle performance and thus optimizing for the fastest lap times. Hello and welcome everyone. So we have covered the final drive ratio, and now what we will be doing one simulation. The objective of this simulation is to find out how sensitive is the final drive ratio or the gearbox ratio or the reduction ratio or whatever you would like to call it, how sensitive it is to the performance of our vehicle. See, there are multiple parameters which can affect the performance of your vehicle. It can be the mass, it can be the wheelbase, wheel track, frontal area, uh, coefficient of frictions in longitudinal direction, lateral direction. But if you look at them, most of these parameters are very much constrained. You cannot change them beyond a certain band. We are constrained to how much your car can weigh, how much can it be in dimensions. We cannot drastically change the coefficient of friction, or so there's a limitation to it. But then there's this one parameter which can be adopted, it's so flexible, which can, with a very small change, you can create a very huge impact in terms of your result. So that is your final drive ratio. So we are using the software from Optimum G called as Optimum Lap. It's a very basic software as such. It's more or less a lap time simulator where your simulation is like a point mass simulation only. So this is an open source software. You can download it yourself and do multiple iterations, and not just for the drive ratio but for multiple other things. It's a good enough software for you to start with, and we will leave the link for this software in the description below, and we will also have one link for how to get this installed. If you have any issues, you can always get back to us. So I'll create a new project. No, I don't want to sign any of these. So okay, I'll create a new project, and I'll name it Nexloop simulation. Let's save it. Okay, so on this home page of this software, you'll find these few icons. Your file, design, simulation, and analysis. In the design part of it, there are two sections. One is the vehicle section, the second one is the track section. For you to build your model, there are two ways. One is you create your own model where you require data for almost everything available, or your assumptions available, and then there is a second option where you can import models of existing vehicles which are already there. You can browse through them on the internet from the database, and some models which you have created, you can also upload them into the database from Optimum G. The same thing goes with the track. You can create your own track, import some tracks, or just upload your tracks to their database. So for now, we will create our own model for the vehicle and import one track. So yeah, let's get started. We'll create. Okay, so now the simulation we'll be doing will be very basic. It won't be also be about a stock car, because what my point is to get through is about final drive ratio. All these variables can change, will change according to type of car or type of vehicle you want to use. So let's keep it very basic. Let's just take have an FSA car. The mass here along with the driver should be under around 300 kgs. Let's keep it two-wheel drive to keep things simple. The drag coefficient should be somewhere around about 0.2 to 0.3. Let's keep it as 0.25. Then your downforce coefficient would be should hover around 0.5, so let's just keep it at 0.534. These are very random values, although they are in ranges which they should be in. And yeah, so your frontal area should be around 1 meter square, so let's just assume from 0.8 to 1 meter square, let's just keep it at 0.8 meter square. And then your air density is 1.2 kg per meter cube. Tire radius, we're keeping it the very standard 0.203 meters. Rolling resistance, we have seen values from lasting from 0.01 to 0.02. Let's just assume it to be 0.01. The longitudinal friction hovers around 1.5. Let's keep it at 1.4. Lateral friction, let's keep it at 1.7. So yeah, this we have more or less filled in the vehicle setup. Now let's get to the engine data, or it will be more prudent if we call it motor data. So the engine speed at 0, we'll have some, let's keep it at 1. We'll have some torque of 81 Newton meter. Then we'll add another value of 1000. Let's keep it at 80. And then we'll have a 2000 graph. Let's keep it at 80 again. And let's add one more. Okay, let's first, we won't delve into it too much. We'll come back to this later. Let's get the other things sorted. Thermal efficiency and fuel energy density is very much optional, so yeah, let's not get into that. Gear ratio, we'll have a gear ratio of 1. We'll try to play around with the FDR. So let us say we start with an FDR of 1.2, and drive efficiency should hover around 95%. So yeah, 95. So we get a very basic curve. Now what we'll actually do is try to fill up the data from a real induction motor. I have a chart with me here, and I'm basically just putting up values from that very chart and trying to fill in this data. So yeah, 3000 will give me around 79 Newton meters of torque. Then 4000 will give me 78.2. okay, 4000 will give me 78.2 Newton meters of torque. And we'll add 5000, which gives me 55 Newton meters of torque. And then 6000 should give me 38 Newton meters of torque. Last, we'll require 2 more inputs to be going in, which will be 28 Newton meter, and oops, we have put them wrongly. 28, yeah. And the last one, which will bring everything to the close, will be 7500. I'll give you 21.4. So yeah, we have put in the data, and ensure that your the one thing by which you can ensure the data which you have put in is acceptable, is that this sort of chart should come up. It's basically your engine torque versus RPM, and the blue line which you can see is the power. So basically we have set up our entire simulation inputs. We are good to go. Before that, before we can simulate, we'll need to have a track. So we, as I mentioned, we will be importing one track. I already have a track with me, which I've imported from the website from OptimumG, and the one which I've chosen is Bodh International Circuit in Greater Noida. All the nostalgia if you've ever been to Bodh International Circuit. So yeah, let's simulate. We have the vehicle ready, we have the track ready. Let's simulate. Here another dialog box opens up. You can select which vehicle. If you have multiple vehicles will show up in this list. If you have multiple tracks will show up on this list. Right now we have only 2. Let's simulate. So yeah, once it's simulated, this result will be created. So you can actually have so many things. You can play around and try to find out the best the best or whatever parameters you want to get a look at. You can plot them on X and Y axis, but right now we are more interested into this table. So now at a gear ratio or final drive ratio of 1.2, we are having a lap time of 142.52. Let's get back to the vehicle. Now I change this from 1.2 to 2 and I simulate it again. Simulate. Yeah, so I go to my table section and just see from 142 it dropped to 130. Let's do this exercise maybe twice more time. Again, going to the vehicle section. Okay, this is, you can actually do this via getting your KPI index simulation, but just to keep things simple, I'm not getting into any complications. From 2 I'll take it to let's take it to 3.5. Simulate. Take me to the table. So okay, again from 1.2 it dropped to 130 and now it is being on the rise again, and I guess it's very much predictable that when we do it again we will be having even slower lap times. So just to reaffirm, from 3.5 I'll take it to 5 and simulate it again. Simulate. Yeah, and yeah, so we can see just by changing a very small number, and even in mechanical sense, changing of gear ratio is not going to impact you as widely or as changing the mass or changing the coefficient of friction is going to. Just by tuning or fine tuning and optimizing on this ratio, you can achieve a better performance for your vehicle. You can, and the difference is very visible. Just from 1.2 to 5 you are getting such varied lap times. Now you can go up to the second decimal of your final drive ratio to optimize, and of course it depends on what are you designing for. Are you designing for peak efficiency or you want it to be a faster vehicle for a particular track? It can, like, this is a very generic, this is too specific to be designing for. Of course you'll be having a generic overview of the vehicle which will give you an idea of what are you designing for. So to put everything in perspective, I would like to conclude I guess the results are there for you to see that how sensitive the final drive ratio can be. Let us observe the map for efficiency of an induction motor. The way we read this chart is we need to locate the operating point of our motors in terms of x and y coordinate, which respond to the corresponding RPM and torque. The color at that point corresponds to the value of efficiency for that operating point. Now if we observe that the motor is at its peak efficiency in middle ranges of the torque as well as RPM. If we can, by some mechanism, try to operate the motor within this band, the results will be very favorable. The way we do it is try to identify the mode, the central tendency, percentile of vehicle speed, and identify most frequent operating area. Fine tune the FDR so that those operating points overlap with the red region of the map. You must have gotten bored by the rants against lower efficiency. You should be. I am not. Because every kilometer we cover in the same amount of energy will have a multiplicative effect. And when we add those kilometers to all the vehicles running on the planet, we are talking about savings in terawatt hours over the future course of time. Let us find out, or at least try to find out the answer for why don't EVs need a multi-stage gearbox. The human brain is designed to make patterns, and once we establish patterns, it becomes very difficult to let them go off. The way a car looks, be it a sedan, a hatchback, a SUV, a pickup truck, or even a chota hathi, it creates an image in our mind. The way cars look or have been structured to look have been specifically tailored to the functions of an internal combustion engine. EVs do not need to have a bonnet. You can easily house the motor inside the hubs of the wheel. We can house the batteries below the cabin floor, which has already been widely adopted. Cars can assume any shape which satisfy the above two criteria. EVs do not need a grill as well. It's my personal belief that we will move to shapes that will supplement the EVs and even better lower drag coefficients. One such aspect of car which is exclusively for combustion vehicle is multi-speed transmission. We from the time we were kids have been so accustomed to running a car and shifting gears. The gear knob or the shift stick has become an inseparable part from cars that even ATs, which is your automatic transmission, or AMTs, who don't even need to have gear knobs, have them as a PNRD switch. For us to understand why don't we need a gear knob, we need to know why it was required in first place in combustion propelled vehicles. Let's study the graph of the engine power and torque versus RPM. Clearly, these somewhat resemble a peak and valley type or a bell curve type of a curve. There is only one peak point and steep falls on either side of that peak. This is in case of both the power as well as torque. And as we previously mentioned that the peak requirements for torque requirements are at the start. Now if we rigidly have only one gear ratio which adapts to our requirements, the torque graph might not support it before and after the peak torque. Thus, we need to introduce multiple gear ratios so that the engine keeps on pumping higher torques at certain RPM, but the speed at fields differs owing to the change in reduction ratio. But that needs us to have a complex mechanism of multiple gears, dog clutches, clutch plates to isolate the gearbox while shifting, gears for smooth shifts, etc. But as you have seen this curve of the motor torque versus RPM multiple times, none of that complexity have to exist here. The motor gives ample torque for a longer duration bandwidth over the RPM. Thus, it has eliminated the requirement of having multi-speed transmission and will eventually lead to the sad demise of the shift stick. While this might be the future, there is an interesting part to how motors have evolved over years and why. We can ponder upon the evolution of motors over the years as promised earlier.